Hello learners, I am Professor Baskar from Geology Discipline, School of Sciences. Today I will be talking about metamorphism. The course code is BGYCT 135 and the course is Petrology. My talk is outlined in the following structure. First I will define what is metamorphism, what do you understand by this term. Then I will explain the factors which affect the metamorphism. Then I would go and explain what is low temperature and high temperature metamorphism. Then I would explain low pressure and high pressure metamorphism, and then I would summarize today's talk. So learners, let us see what is the meaning of metamorphic rocks. They originate when a pre-existing rock or protolith undergoes a solid state change. Please remember, metamorphic rocks are formed from pre-existing rocks. They are formed from pre-existing igneous, sedimentary, or even it can be a metamorphic rock in the sense that it can change its grade. And here the most important thing is that it should be a solid state change. That is, there is no melt stage involved. These rocks are subjected to high temperature and high pressure in the presence of fluids that typically comprise H2O and CO2 and some other ions. The term metamorphism is derived from a Greek word meta means change and morph means form. In a way, the form is changed. This forms when the pre-existing rock or protolith undergoes a solid state change, as I mentioned, without melting, in response to elevated temperature and pressure in the presence of chemically active fluid. Now, this is an isochemical process. That means the bulk chemical composition of a rock body is more or less unchanged from the protolith or the original rock. That means, by and large, the composition remains same, but there can be change in certain aspects like texture or structure, etc. Now, what is the meaning of the term protolith? Protolith is the original rock before metamorphism. The low-grade metamorphic rocks preserve the original textures of the rock, and therefore easily you can identify the protolith. Whereas when the metamorphism grade rises because of the increasing temperature and pressure, the metamorphic textures which are typical can replace the original rock texture. In that case, to identify the protolith, we use mineralogy or bulk chemical composition to find out the protolith. Now, there are different kinds of protoliths which are there. One, they can be quartzo-feldspathic, they can be granitic rock or arcosic sandstone, they can be peletic, they can be shales and mud rock, they can be calcareous, calcite and dolomite, they can be basic or ultra basic in composition, for example, basalts and gabbros. Ferruginous, they can be Fe-rich cherts or ironstones. So these are the original rocks, for example, from which the metamorphic rock can form. Now I am giving some examples of metamorphic rock from the protolith. Now here the protolith is granite, which is transformed to schist during the process of metamorphism. You can see the diagram. The left hand side is the granite and the right hand side is the schist. And the composition is the same, but the texture and structure is changed. Similarly, sandstone is a sedimentary rock. It is metamorphosed to quartzite. You can see the diagram which is on the screen. The third one, the composition of limestone and marble are same. Limestone is a sedimentary rock. It is metamorphosed to marble. And the hand specimen are given some photograph of metamorphic rocks, slate, which you are familiar, which is used in blackboards. It's in the form of, you can see some layers. Then you have phyllite, then you have schist. You also have different metamorphic rocks based on the texture like gneiss, quartzite and marble. So these are formed from different kind of protolith rocks. Now metamorphic rocks are characterized mainly by changes in one, mineralogy, structure, texture and sometimes changes in chemical composition may also take place. Now, what is the definition of metamorphism according to IUGS subcommission? It is the solid state transformation of rocks from increased heat and pressure deep underground. Because the same rocks can undergo change in temperature and pressure conditions, they are transformed. This definition prohibits significant changes in bulk composition. Now, there is also metamorphic rock in which some chemical composition change can take place. This is called as metasomatism, and metasomatism is the chemical alteration of rock by fluids. This process replaces one rock with a different mineral and chemical composition. Now the original rock minerals can dissolve and replaced by new minerals while the rock stays solid. Please remember, here there is no liquid form in the entire stage. It is replacement of the mineral by another mineral and there is a change in composition. Now metamorphism, the minerals and rock change during metamorphism until they reach equilibrium. Because metamorphism occurs under changed pressure and temperature conditions, the rocks tries to regain the equilibrium and they undergo metamorphism till they are in equilibrium. Now metamorphism is not limited to earth dynamics at tens of kilometers. It can happen even near the earth's surface. You also know the formation of anatectic melt during high stage metamorphism. Now, what are the factors which affect metamorphism? One, obviously temperature. Second, pressure. Third, shearing stress. And fourth, chemically active fluids or gases. Now, temperature is the primary factor in metamorphism. Temperature is the one which supplies heat energy for chemical reactions, leading to recrystallization or new mineral formation. It is very obvious that if you increase the temperature, the existing rock will adjust itself and metamorphose to the new existing temperature. Now, the question is, from where does the sources of thermal energy come for metamorphism to occur? All of you know that the heat generated from the deep interior of the earth is left over from accretion of over 4.5 billion years ago. Still, the heat is there and that is a source. Second, there is decay of radioactive elements, long-lived radioactive isotopes that generates heat. And also you know that frictional heat is generated along faults or shear zones and these are located to near surface regions. Then again another source of heat can be the latent heat of crystallization from igneous intrusions and magma. Now, the rocks which undergo regional metamorphism in deeper regions of the lithosphere are deformed and the mechanical energy involved in thrusting is also transformed to the thermal energy. Now, how does the conduction of heat take place? Conduction is the method of heat transfer. Heat transfer takes place through conduction and it takes place obviously from higher to lower temperatures. Now, heat is also transferred from the interior of the earth into the surface by the production of heat due to radioactive decay of uranium, thorium and potassium. These are the high heat producing elements. Now, there is a term which is called as metamorphic grade. What is metamorphic grade? The grade of metamorphism increases because of geothermal gradient and pressure on a body which increases with depth. I will explain the term geothermal gradient in the next slide. As we go deeper, the temperature increases and the pressure also increases. So the grade of metamorphism changes. Metamorphic grade refers to temperature and pressure conditions for rock formation. If you see this diagram, you have low grade metamorphism, lower temperature and pressure. You have intermediate grade, which is intermediate temperature and pressure, high grade, which is higher temperature and pressure in the diagram. Here what you have to understand is that after the high grade limits, you will have the partial melting taking place. That becomes the igneous domain. And below the low grade, you have the diagenesis which occurs in sedimentary rock. So you can see there is a limits of temperature and pressure for metamorphism to occur. Now, what is geothermal gradient? Now, igneous intrusions carry heat from the mantle to crust because magma is rising. Magma is a source of heat. Because of buoyancy, it is rising to the surface. It invades the country rock. Because of that heat, it has a baking impact on the cool rocks, and that causes contact metamorphism. Now, what is geothermal gradient? As you go deeper into the Earth's surface, the rate of increase of temperature in the Earth with depth is called geothermal gradient. And on an average, it is between 20 degree to 30 degrees centigrade per kilometer. The rocks formed at the Earth's surface are transformed to greater depths and experience a gradual increase in temperature. Now, there is another term which is called load pressure or P load. It is the stress on rock causes metamorphism and alters its compositions, minerals and texture. Metamorphic rock formation, as I said to you, is influenced by temperature, chemical composition, chemically active fluids and pressure. Now, this load pressure is nothing but the lithostatic pressure or the total pressure which is equivalent to the pressure on a given volume of rock, or you can say in other words, the load of the overlying rock or the lithostratigraphic column. Because of the weight of that overlying rock, it causes pressure on the underlying rock. The pressure from the load causes the formation of dense anhydrous minerals in deep layers. Now, because of this pressure, there is increase in density of the minerals which are found lower and they become anhydrous. Now, this confining pressure grows with depth because of rock weight. It is obvious, the greater the depth, the greater will be the overweight of the above rock and greater will be the pressure, and it affects uniformly and increases with depth similar to temperature. Just like temperature increases with depth, the pressure also increases with depth. The metamorphic rocks from the deep earth obviously will be denser than those from the shallow crust because of the pressure, the squeezing takes place, and also the water gets squeezed out, it becomes anhydrous. Now, if you see this diagram which you can see on the screen, in the first photo, you can see random orientation of minerals. And because of the weight of the overlying rock, there is pressure and there is preferred orientation of minerals. And these get oriented in the direction of maximum stress direction. So you can see flattening and orientation due to pressure or stress. There is another pressure which is called fluid pressure. This is because of the water which is present in the rocks. Water from the meteors, groundwater or the sea, upon meeting the magma, carries a mix of metallic cations, dissolved compounds, ions and volatiles. Such chemically enhanced waters play an active role during metamorphism. It is not only water, it has dissolved chemicals in it. And water speeds up the chemical reactions in the mineral by dissolving ions to create new minerals. The geothermal gradient indicates that temperature and pressure increase with depth. Now, the released fluids, what you see, are chemically active and often act as a catalyst, reactant, or product during metamorphism. Again, the breakdown of hydrous mineral progresses with increasing burial depth because of the increasing pressure and temperature in the metamorphic settings. Now, what happens when there is a presence of a free fluid phase? The presence of a free fluid phase helps define fluid pressure, pressure fluid, or PH2O in case it is a pure water, which plays an important role in controlling the stability fields of hydrated phases such as micas and amphiboles and carbonate phases when the fluid is carbon dioxide. So you can see the stability of the minerals get affected if there is water or there is a fluid or there is a carbon dioxide dissolved. And there is another kind of pressure which is called shear stress. Now the solid rock under pressure at depth is normally in hydrostatic equilibrium. That means the stress from the external force is isotropic. That is, at all directions it is the same stress. But if this stress is in a particular direction, for example, when plate tectonic comes into play with converging lithospheric plates, when two plates come and collide with each other, the stress no longer remains isotropic. And what happens in one direction, the stress increases, and that is called the shearing stress, better known as deviatoric stress, and is maximum in planes at 45-degree angle to the principal stress. So because of this directional stress, what results is that metamorphic reactions are accelerated due to speeding up of ionic diffusion, which would otherwise be too slow to be effective. Now, this shearing stress increases the total area of the grain surface, causing a flow in mineral aggregate and renews the surface contact between the grains. Here you should understand that the temperature range of stability of some of the minerals are extended due to the shearing stress, because it also depends on the stability, depends on the shearing stress. It decreases the melting point and increases the solubility of the minerals. Now see this diagram. You can see one is the normal stress, which is same in all directions, and other is the shear stress, in which it is directional, and in one direction it is stressed more, and that results in the shear stress, which changes the stability of the minerals. Now, there are certain things which you should understand, which are called limits of metamorphism. Pressure and temperature governs the limits of metamorphism. And let me make it clear, learners, that metamorphism does not include weathering, diagenesis. They are part of sedimentary process, and melting is a part of the igneous rock formation. Metamorphism occurs at temperatures and pressures higher than 150 degrees centigrade and approximately 300 megapascals. And diagenetic processes occur normally below 150 degrees centigrade and pressures below 300 megapascals. So you can see that transition is taking place from diagenetic process to the start of metamorphism. And in most of the rocks, the phase transformation begins shortly after sedimentation and continue with increasing burial. And sometimes it becomes very difficult to find the exact boundary between diagenetic process and metamorphism. And in silicate rocks, the lower temperature limit of metamorphism is around 150 plus or minus 50 degree centigrade. And if you see the beginning of metamorphism, it is marked by the first appearance of the following minerals like prehnite, pumpylite, paragonite, lawsonite, glucophane. These are some examples, and the occurrence of these minerals tell you the beginning has taken place of metamorphism. Now, what is the higher temperature limit? Once it is more than the metamorphic part, melting takes place. The beginning of melting is a part of metamorphism at the highest grade as long as the rock continue in the solid state. At higher temperature, the melting of the rocks will be initiated, and these temperatures of melting will define the high temperature limit of metamorphism. And obviously, the factors on which the melting temperature will depend are rock composition, the nature of the rock, the pressure under which it is going this temperature change, and also the fluids, the water which is present can affect the stability of the minerals. So you know the low temperature limit and the high temperature limit. Now I will talk about the low pressure limit and high pressure limit. Now the fluids in the porous rock is called pore pressure, and water speeds up the ion exchange reactions. Now the weight of the rock causes load pressure, bringing minerals into contact. And you can see high pressure over short periods causes rock to fold and fault because of shear or directed pressure. So whenever folding or faulting takes place, it is an example of directed pressure or shear stress. And though the lower pressure limits of metamorphism are undefined, metamorphism in contact aureoles may occur at the surface pressure of few bars if the magma rises towards the surface. Because the magma is hot, it bakes the surrounding rock, and this causes the metamorphism. High pressure limit. For a long time, we believed that the highest limit of pressure in metamorphic crystal rock correspond to the lithostatic pressure at the base of a normal continental crust of average thickness of 30 to 40 km, and we thought that this does not exceed around 10 kilobar. But as better calibrations were available, in some metamorphic mafic rocks, the mineral assemblages often recorded pressures of 15 to 20 kilobars. And you can see the metamorphic mafic rocks of high density and consequently formed of high pressure were said to be equivalents of basalts, and they were called as eclogites. They are formed under extremely high pressure conditions. Now, the summary of my talk, to sum up, is metamorphic rock is formed from the recrystallization of pre-existing rocks, either by mineralogical, chemical, or structural changes. And why these changes take place, mineralogical, chemical, or structural, in response to the changed temperature, pressure, conditions, or the presence of chemically active fluids in the Earth's crust. Now, this is a part of the rock cycle, and rock cycle is a continuous process which is related to plate tectonics, in which one type of rock changes to another type. An igneous rock becomes a sedimentary rock, or it can be become a metamorphic rock, or any type of rock can be changed into any type, and this is called the rock cycle. It is the cycling of materials within the Earth's crust, and that is because of the heat energy which is available. Now, rock cycle can start with the cooling and consolidation of magma derived from the mantle, which are subsequently exposed to new conditions, the atmospheric agencies, to form sedimentary rocks under normal temperature and pressure conditions, or metamorphic rocks under increased temperature and pressure conditions. So learners, thank you very much for a patient hearing.